All right, let's get started. So last week we left off with a long discussion of Paxos. But the observation that I'll make is that Paxos is probably the far end of the complexity spectrum in terms of building distributed systems. So today we'll start talking about alternatives, different ways of solving the same basic problems. Yes?
The slides is not released yet.
Did I not put them up? Sorry, I thought I had. Okay, my apologies. I'll put them up after class. So, before you've forgotten it, just spend a couple of minutes, try to explain to each other the observation that we were talking about last time, which was in inflexible Paxos, all you need is to ensure that quorum of phase 1 and the quorum of phase 2 intersect with each other. They don't have to be the same groups in them. They can be different groups. You can have different quorum definitions there. Just to cement that idea before we leave it. So, just 2 minutes. Alright, so you have that conversation. Well, probably about 30% of people had that conversation. How many of you feel like you understood why you needed those two different quorums that will have an overlapping element, overlapping member? Anybody? Sorry?
I said Bueller.
Bueller.
Yeah.
How old are you?
Younger than you.
Yeah, but that's like old reference.
Sure, it's a good movie.
Maybe before you were born.
Oh, yeah.
Well, we know who the troublemaker is. So the observation here is that The reason we need that is so we know that the most recent decision of a leader is always in the intersection. So a new leader can always figure out what the last decision was. That's the purpose of the whole intersection. That's what we started with. We took the very simple case. We said, look, anything in this one form set that overlaps gives us that common element, and that's how we're going to ensure that we know what the last decision was. Then when we generalized it, we said, well, we're going to start stacking our turtles. Oh, look, all we need to do is make sure we still have a common element across our stacks, and we can still do exactly the same thing, which is we can still figure out what the last decision was. So multi-Paxos and flexible Paxos and most of the Paxos implementations end up being about picking a leader. But is electing a leader the best choice? I mean, I'm not trying to make that a political question, but obviously one emerges from that. Is electing a leader the only way to get strong consistency? How many people think it is the only way to get strong consistency? How many people think it's not the only way? Okay, a couple people have peeked a little bit ahead, right? And then there's the vast majority who were like, I don't really care. It's almost lunchtime, I'm hungry. Quorum-based consensus is actually expensive. That's one of the reasons that we ask this question, because many times what we build are focusing on optimization. Now, usually what happens is people start out with really simple models and they find out that they kind of suck because they're slow, because they're not efficient. Is there anyone in here who took 313? I think it's a prerequisite, right? Do you vaguely remember this thing called virtual memory? Before you had virtual memory, what you actually had was physical memory. And everybody just simply used physical memory. And in, must have been the late 1950s or early 1960s, somebody built a machine called Atlas. And they said, you know, the problem with using physical memory is that it's a finite resource, and if we don't use it very well, then we really can only do a limited number of things with it. But the reality is, imagine that you're sitting at your desk or you're sitting on your couch or wherever and you're studying. Do you need all of the textbooks for all of the classes that you're studying sitting there in front of you right now? Of course not. What you need is the material that is pertinent to what you're doing. But we don't really know what that is. In a hardware architecture, in a machine, we just simply know that, hey, you're accessing some stuff. I don't know what it is. To me, it's just a blob. It's memory. It has no inherent usefulness or meaning. But we can optimize around that. What we can do is we can say, what I've noticed, though, is that you keep reaching for that textbook. So that's the textbook that I'm going to keep in memory, and the rest of it can be sitting over in the other room. If you need it, we can go fetch it. That's the idea of demand paging. This is exactly what we do in systems over and over and over again. So we've solved this very general problem. We've done it in a way that is extraordinarily scalable but really complicated. Can we simplify it? Can we make it more efficient? Can we come up with a way that we don't need to do any voting at all and still guarantee safety, still guarantee consistency? So let's replace voting with structure. It's discipline that matters. Now suddenly I'm feeling very German. Structure. It's important. UBC exudes structure, doesn't it? Often to the point where you sit there and you go, why? But that's a different problem with structure. Sometimes it becomes a little too constraining. But in this case, we're going to ask the question, What if we just simply don't allow conflicts? Everything goes to one place and it decides what the actual outcome was. That's easier, it's simpler for us to implement. But we still want redundancy. We don't want a single point of failure. So what we could actually do is we could build a little chain. So in primary backup, we had a 2-element chain. We had a head, we had a tail. What happens if we go to 3, or 4, or 5, or 10? What can we do with that? And that's what we're going to be exploring today. That's what we're going to talk about. The first one is called chain replication, and then there's an interesting variation on that, because of course we have to make things faster. We go back to efficiency. So we trade back and forth between simplifying models and making them more complicated to improve their performance. So how about if the write goes to the head, and then the head sends that to the next copy, and the next copy sends it to the one after that, and the one after that sends it to the tail? What can we do with that? In this case, we can say that the transaction or the operation, the replication, has committed when it hits the tail. While it's in the middle, it's kind of like we're still in the proposing phase. It's just, think of it logically. It is everybody has to agree that this thing has been properly recorded before we're going to make the claim that it is in fact a decision. It's kind of back towards 2PC in some ways, but we're replicating here. 2PC was about making different but interrelated decisions. This is in fact just simply keeping multiple copies of the database in sync with each other. So in 2004, and that's probably almost within your lifetime at this point. So we're almost getting to like ancient history of land as opposed to, fossilized. Ferris Bueller's Day Off. What is that, like 1980s?
86.
There we go. Ever seen Star Wars?
What's that?
It's this movie I actually saw in the theater as a kid. That's how old I am. And you can't see that version anymore because Lucas basically destroyed it and made other versions of it. In chain replication, this is exactly what Van Rennes and Schneider said. A client sends a put to the head. It just knows the head because it's part of the configuration. That's part of that structure I'm talking about. So the configuration says send your puts here. So this is a write. Then it goes and it propagates that write through the chain. The tail is the last one to see the write. And once the tail has in fact recorded that write, we now have an accepted put. The tail can send a message back to the head and say, okay, I got it. This is now propagated. This is really simple. Compared to Paxos, where we're doing things asynchronously or whatnot, this is very simple to look at and to say, okay, I can see this. What do you see that's wrong with it? I'm patient. I can wait.
Intermediate nodes don't know what's going on. If, for example, the tail doesn't commit, doesn't send an acknowledgement to head.
Okay, so we have some failure conditions that we have to worry about. I was actually not even getting to that point yet, but that is a good point. What about in the common case where they're all working and they're forwarding these messages? Why would you want to use something more like Paxos than you would use this?
This is
I was going to say,
Right, you're slowing it down. Now the amount of time it takes to commit that transaction is in fact completely additive. And having been doing a lot of work with additives, everyone knows that in fact that has quadratic performance, right? Because n, let's see, the sum of 1 to n is n times n plus 1 over 2. and that's order n squared. So you're like, okay, well, at 5 it doesn't really matter because that's 5 times 6, that's 30, so divided by 2, it's 15. So it's a little bit slower, but it's not that bad. We can probably live with 15x. Especially if we're talking about milliseconds, right? 15 milliseconds to do this, I can live with that. So this is actually a really good solution when you have a modest number of nodes in a low latency environment. Because you're avoiding the extra complexity and the cost of electing a leader. Because that leader election isn't free. And this is what happens when you start building distributed systems. You go, oh, this is cheaper and this is more expensive. So the trade-off is often, I will do the rare thing that's more expensive and keep the common path as cheap as I can. Until the tail acknowledges it back to the head, that put is not committed. The client doesn't get a return from the put request. Now the client gets a return for the put request. Anybody else who asks for this value is going to see the value that the client put in there. But while it was in those intermediate states, what does the client see? I mean, the correct thing is it sees the old value. It doesn't see the new value because the new value hasn't committed yet. And when I step back away from this and I go, okay, this is a distributed system and I need a consistent cut, and it sent that message and that value is here, so it could have seen that, I'm okay with that because that is a consistent view of the world, even if the world changed a moment later. When you go and you check a value in memory, it can change right after you check it, immediately. Because it's not constrained, it's not tied down. That's okay. It doesn't mean the value you read 50 nanoseconds ago, which is now changed, was invalid. At the time you read it, it was the correct value. That's okay. That's the guarantee that we're providing. We're giving a linearization, but we're not guaranteeing that the message that tells you what the value was arrives before the actual change occurs. We don't have a global clock. Now here's the interesting thing. If you want to do this really simply, you just have the clients that are doing reads read from the tail. Because if it's in the tail, the decision's already made. We don't have to do any quorum reading, we don't have to do anything fancy, we just simply read from the tail. And this, by the way, is in fact after Lamport published the part-time parliament, which is the description of Paxos. So Paxos was already known at this point. And everybody knew that Paxos was not that hard conceptually, but it burns you in the details when you start building it because you have to think about the ordering of events in an asynchronous system, which just, it takes a while to wrap your head around it. I think that I've found a lot of people who don't ever wrap their heads around that very easily because they're not used to that kind of asynchrony. Since the tail only has the committed writes, it never holds a pending value. It's always safe to read the value from the tail. So now we have a nice simplification there, and the nodes in the middle just simply become backup copies, which are going to allow us to deal with partial failures. This gives us strong consistency. We don't have any voting. We only have a single round trip for the reads, because the client reads from the tail. This actually gives very efficient behavior. Yes, writes are slower, but the reads are faster. And that's what I said, the optimization. If writes are your uncommon path and reads are your common path, and that is a very common workload, you want to use something like this because it keeps the read cheap even if the write is more expensive.
What if writes are in progress?
The tail hasn't seen it yet. That's what it means to be in progress, right? So that's the whole point. The client gets the agreed upon value because everybody else knows that value is proposed for a change, but the change hasn't been adopted. That's why I was saying earlier that this is okay because when you read a value, it can change a moment later. That's considered to be acceptable behavior. If you need higher level semantics over that, that's when you build linearization, you build blocks around things.
So this is different from Paxos, because in Paxos it like waits, right? Until the value's like confirmed.
In Paxos, the learners actually do block and wait until the outstanding decisions have been made. So yes, so this gives you a different result than you would get with a Paxos system, but it's still a correct result. Great question. All right, so in Paxos, writes are done using a quorum model, but it's in parallel. In chain replication, writes propagate sequentially, so which has lower write latency. Hopefully this one won't be too hard since I've kind of beaten it to death already. But let's take 2 minutes. You guys talk about it and try and reinforce why.
So this isn't those nodes are not, it's only like this, right? Because they're not only connected to the one side, they're connected to all the
We haven't connected to anything else yet. I mean, in our model, we've just simply propagated in one direction, but in fact, what we're going to recover from failures is going to be that this is a recognizable with a knowledge. Because those nodes aren't prevented from talking to each other, it's just that in the common case, they couple.
This is basically, so propagation is like, just duplicates the same process.
Yeah. It's literally, here's what, and the reason these key value sources is because they're really easy to understand. This is a single atomic operation. I don't have to worry about the higher level stuff where things have to be consistent with each other.
We also
Lower right,
always
the throughput.
reads correct. We always write to the head.
You always write to the head,
And
and
you
you
never
say,
read from the head.
no, you
We
read from the tail.
decided to read.
You always read right. You read from the tail, you write to the head. Okay. And that's what makes CRAQ, makes chain replication really easy. But you're already thinking the right thing, which is, well, why can't you read from the middle or something?
Yeah.
And we're going to get there. Okay. Good morning. You know, the day has started off extraordinarily well. Almost any day that you realize that you might have actually saved a measurable percentage of the carbon load in the world. A good one. All right. So, who has the lower right latency? You've got a binary choice here. Yes, 50-50. Go for
Paxos.
it. Paxos. Why?
Because it's in parallel.
Because you've got the parallelism in there. Anybody disagree? Anybody agree? I see some hot heads nodding, but I don't know. Because, of course, we should always elect these things. We should make decisions about what is true or false based upon popular opinion, right? We know how well that will work. Which one has a better read latency?
The chain replication.
Why?
Because you can directly go down to tail and tail.
It's one message. You don't have to read a quorum. If that were a five node Paxos instance, you'd have to read from 3 of them. Now maybe that read would be behind somebody else, but you still have to wait for that consensus. So in Paxos, the write latency is approximately 2 round trips because you have a prepare and accept phase, but those go on in parallel. In the reads, you have to ensure serialization because you have to make sure that you're serializing against the current leader and or a read quorum. In chain replication, write latency is in fact multiplied by the length of the chain and the hop latency. So the read is 1 hop to the tail, the write throughput is in fact quite high because of the pipelining. So reads are fast. The write latency is higher, but the write throughput is actually quite good. So if you have high sustained write loads, chain replication could be a good choice. So the interesting point here is the pipelining comes because in Paxos we make individual decisions. Before we can't have multiple simultaneous outstanding decisions. Well, we could, but that would make it even more complicated than it already is, and your head will explode. But every node is always busy processing or forwarding writes in the high load situation when we've got a continuous high pressure stream of changes. You're building the X, formerly known as Twitter, fire hose handler. That's typically the real world case that breaks people, because the output of X, FKA, Twitter is literally measured in millions of events per second. God knows why. I mean, you might be old enough to remember Ferris Bueller, but you probably don't use X, right?
I call it Twitter. That's how old I am.
Well, that would mean you're over 4.
Surprise.
I don't know, did your class have one of those like 13-year-olds who is doing university? Those are always interesting people. I had one of those in one of my math classes. And the worst part was like his dad had written a textbook. So the latency itself is worse, but the throughput can actually be better. So that's an interesting spectrum on the trade-off. That's an interesting trade-off on the spectrum of choices. Yeah, that's a better way of putting it. Why is this strongly consistent? Because all writes enter through the head. They're totally ordered in a trivial sort of way. It's not hard to look at that and say, of course, they're going to happen in the order in which they were presented to the head, and they're going to show up at the tail, because everybody is processing these in pipelines. They're FIFOs. There's nothing to cause out of ordering them. So the tail is the commit point, and only committed writes become visible. So the reader goes to the tail, because now the reader sees exactly the decisions that have been committed. Whereas in Paxos, we have to get ballots to establish ordering. Chain replication has no competition. So whereas Paxos had issues with liveness, the issues here are in fact just about node failure, causing us problems with liveness. But we've got 5 points of failure now instead of the minority, the subquorum points of failure that we had in Paxos. So this gives us the same effective outcome. We get an ordering of the events. Question.
Would you use this like by itself? Because like, what if does this account for failure? Like if the head fails, for example, like
We haven't gotten there yet.
Okay.
But you're asking the right question, which is, okay, great, you showed me the steady state. But if you're sitting there already thinking, but what about when things break, then good, because that's the framing that I tried to use for the whole class, which is, it's easy to get the fast case where everything's hunky-dory and the world is fantastic and everything goes your way, but how do you deal with it when things start to fall apart? And we're going to get there. So, in the chain system, our invariant is always, it has to be propagated across everything. And then we got a nice little formal statement adapted. In other words, all the tail contains all of the states that are contained by the previous node, which contains all of the states that are contained by the previous node. If there's nothing flowing through it, then those are all equal. The only time that one is a subset of the other is when there are outstanding messages. And now we get to failure. What happens when a node in the chain dies? There are 3 cases that we're going to analyze. What happens when the head fails, what happens when the tail fails, and what happens when something in the middle fails. So this is where we now have to do a little bit of magic, because remember, in Paxos it was able to recover from a leader failure, but here we don't have a leader. So what we have is a leader that we're going to call a configuration service. I think that the term master fell out of favor somewhere along the way because it implies involuntary servitude. Slavery. Both Paxos and Raft actually manage the configuration separately. Paxos Lamport goes through great details about, essentially puts another turtle on there. The first turtle is the configuration, the second turtle is the leader, the third turtle is the actual decision on the current slot in the wall. So, the tail fails. Well, this one, the recovery is, you just change the configuration, you say, oh, well, the tail failed, I'm going to now make S4 the tail. That's the single node failure case. As long as we can keep one of these things running, we can recover from them. And ultimately, what's going to end up happening, like in the case of a partition, this partition is a really interesting case, it's going to be the nodes that are still visible to the configuration service. Because if the configuration service can't talk to a node, it's going to basically say, it's dead. I can't use it. So I can't use it in part of my configuration. So the tail failure is really the simplest case for us to deal with. We just promote it to the predecessor. What happens if the head fails? Well, this one means that we now have to actually move here. Anything that was in S1 that hadn't been forwarded to S2 hasn't been acknowledged yet. And clients still operate under the assumption that if they don't get an acknowledgement back after a while, they try again. They use the same sequence number so that we can detect when, we've already seen this in process, but standard networking kind of sequence number. And since those were never committed, they'll just get retried. And that's why we can actually safely switch to S2. But the uncommitted writes could be lost, that's okay, the client will retry. The client doesn't know necessarily, the client knows it needs to retry because it didn't get an acknowledgement back. If the acknowledgement was what got lost, then trying the same operation again, whoever receives it will send an acknowledgement back and say, yeah, we already got that. So those are idempotent. This is the interesting case. What do we do when the middle node fails? Or one of the middle nodes, because there's 3 middle nodes. Well, what we're going to do is we're going to basically just take it out of the configuration. We're going to say S2 now points to S4, and anything that was pending inside of S3, same thing as if the head died, which is it hasn't committed, so the client will eventually retry it, and we will recover. What S2 has to do here, though, is it has to actually coordinate with S4 to know what needs to be sent. Because S5 would have been sending its ACKs to S1, so S2 won't necessarily know what has disappeared between it and S5. So it will have to do some coordination here. So there's a little extra protocol wrinkle there. But it's okay because S4 can receive things from S2 multiple times because again they have a sequence number in them, so we know if they've already been applied. So we kind of have this idea of an in-transit window where we're uncertain, and we can send that everything in that in-transit window again and know that they're idempotent. If they've been applied, we don't reapply them. In the implementation of this, you get to build that knowledge buffer of the in-transit operations. And that becomes part of the complexity of implementation. But the protocol is fairly straightforward here. When S4 catches up, the chain seals itself, and life returns back to normal. So we get a bit of a slowdown here when there's a node that crashes. Okay, fine. That's perfectly reasonable. We have to do a new leader election in Paxos when these kinds of things happen. So here we have to do something comparable. So let's do another checkpoint here. Make sure people are following along here. So S3, the middle node there, crashes. We have 2 writes that were in S3 but hadn't reached S4. These are the questions you should be asking asking, try to explain it to each other, see if it makes sense. If it doesn't, then I need to do a better job of explaining it. 2 minutes.
It's fine, because S2 would.
You need to talk to yourself.
Yeah.
Sometimes it's the other way to get in the knowledge of
But S2 crashed.
Sorry? I talked to Quad, which is completely different.
The client can just use it as this, right? That's what we said, is if they didn't get back. The client
Right, so the client will, usually what happens is the client will try to send you an S1, and after a while, it'll say maybe the configuration is broken, so it'll go and it'll for the configuration hasn't changed, it's still trying S1 and it's back. So, yes, this is, now that's a really good question, because it gets into the, how do I actually influence the world? And there's always that balance. How many times I keep trying before I go to these other operations? But it does work. Eventually,
So there's a configuration somewhere.
yes, that was the configuration manager, the master. Basically, that's what they replace the leader with. Makes sense? Good. Which one of All right, so first question, were W7 and W8 committed? That should have been a pretty easy one because you look at it and you go, it hadn't been sent to S4, so it can't possibly be committed. And that's the right answer for that. Does S2 have them? Why?
Because they were in S3, and if they were in S3, they
Had to have come from S2. Correct. What does S2 need to do?
connect to coordinate with S4.
It has to figure out between it and S4 what S4 doesn't have that S2 has. So that's just the in-flight window. The protocol doesn't define how you do that. It's left as an exercise for the reader. You know, the thing that you'll spend 3 months building, because how hard could this possibly be? So a key here, and someone asked me about this, is how does, what does the client do when the head dies? How does it know that the head has died? How does it know where to go? And the answer is it goes back to the configuration server and says, what's the current configuration? And that can take a little while, because you don't want to be constantly reading the configuration. And you don't want to immediately jump to pounding on the configuration manager. But if you waited a period of time and you haven't received an answer from S1, you can go and say, is S1 still the leader? And if it's not the leader, then you know what the new leader is. You now send the request to the new leader, and the system heals. The decision on how long to wait is not a protocol level decision. It's a pragmatic decision you make about what is appropriate for my workload. Now the flip side of this is, and this will make you laugh, often what ends up happening is the configuration manager becomes a Paxos implementation. That's a very common way to structure these. Because if I have a single configuration manager, it becomes a single point of failure. I don't want a single point of failure. So in fact, if I build a Paxos-based configuration manager, the greater complexity, the higher overhead, it really won't matter. And so we get something like Zookeeper. which is a configuration manager. Anybody use Zookeeper? Anybody want to work as a Zookeeper? Apache Zookeeper is in fact a configuration management service that is built on top of Paxos. It's built on top of a Paxos implementation. Like I said, configuration service is typically Paxos. I mean, Raft just recreates the problem because Raft uses Raft still has a leader, but the way it chooses a leader is slightly different. So chain replication doesn't eliminate consensus, it just simply limits it to configuration changes. We're using Paxos where it is strong, good recoverability, and we are mitigating its cost, because Paxos is complicated and potentially slow, but configuration changes are rare events. So we don't need it to be fast, we need it to be right. There's an interesting bottleneck here, which is the read side. In vanilla chain replication, that means the original description, reads become slower because even though we have 5 nodes, we're only reading from one of them. So that one ends up getting bombarded with all of the read traffic and becomes the bottleneck. So a read-heavy workload, which in fact is the most common case, it's not uncommon for people to look at 95% read, 5% write workloads because they happen in the real world, like Twitter, where Twitter has these things called trending, whatever they call them. And those are all served by a key value store. And that key value store has hotspots, like really hot hotspots. So whatever's trending is 90% of the actual workload. We're only hitting 25 keys over and over and over again. And that's kind of the worst case read workload. So not only is it heavily read oriented, but it's heavily read oriented and only a tiny fraction of the things that could be read are being read. Has anybody in here heard of the Pareto? 20% of the students in class cause 80% of the problems. And how many times have you sat in a class where you know there's like a handful of students who answer all the questions and have all the opinions and know everything, and everybody else is just sort of lost? That's the Pareto rule, which is usually 80-20. It doesn't have to be exactly 80-20, but it's in a power law distribution is the general mathematical term for that. In a power law distribution, you basically have a small peak and then a bell shape that comes out of that. And how steep that bell is defines how extreme the distribution is. And you'll see them over and over and over again when you build systems. They happen all of the time. So the question is, could we actually spread our reads across the chain, because we've got 5 nodes here, and not sacrifice strong consistency? And so in 2009, now I think that's probably, it definitely has to be after everybody in this room was born, since we don't have any 13-year-olds. Actually, that's 17 years ago, so anybody who's under 17. The key idea here was that you add versioning. And so what you do is you can read through any node, but you have to do a version check. So every node has a clean version. That's the latest version that is known to be committed. Now, do you notice that we've just snuck in here? See, before, we didn't have to propagate the, oh, it's been written at the tail. We didn't have to propagate that through. Now we have to propagate that through. Because now we need to know when the tail has committed it. But it does solve our healing problem. Remember when we had a node in the middle die and we had to heal that? Now we actually know what operations were still outstanding, and we can send those again. So that makes the repair in that case easier. So we have a clean version and a dirty version. A dirty version is the version that I last sent to the next node. I've seen this version, and I've now sent it onwards. Actually, maybe the strictly correct way to say that is, it's the last updated version I've seen, whether I've sent it or not. There, now I've closed that race condition. The small race between receiving it and sending it. It doesn't matter to the analysis. So, if you read at a particular node, I was just waving goodbye. I wasn't making a comment at all. I figured maybe, you had to go fix the node in the middle. If you read from a particular node, you just look and see, is the latest version clean? If it is, you just return it. Fine. Maybe somebody up the stream from where you're reading has a dirty version, but you have returned a value that would have been returned by the tail. Life is good. This doesn't change the behavior from when we just returned from the tail. If the latest version is dirty, though, then you have to actually go ask the tail, what's the latest version number for this value? In other words, you go read from the tail. So if the intermediate node says, well, this was in flux, you probably need to go talk to the decider, which is the tail. Okay, we did 2 reads instead of 1. But most of the time, especially as the database gets larger and larger, almost nothing is changing. That's that power law distribution. Most values are written once and never changed after that. A few values will be written and changed frequently, boom, 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 while they're hot. And then they go cold, and they won't change again. So this optimizes that read workload. With the cost that, unfortunately, in the hot case, in the hot path, we probably will have to go and do 2 reads. That's still a tiny percentage of the total number of reads that we do. So it does, in fact, slow down the hot path, which isn't great, but it speeds up the path for everything else. And again, this goes back to why building these kinds of systems is not a simple paint-by-numbers exercise. Everything requires that you make trade-offs. It's almost like real life. Do I go get a job? Do I go to grad school? Do I just simply move to a beach someplace and soak up sun and sponge off of tourists?
How does a particular node know the value that it has is a clean version?
Because we have to send a message back through, right?
So each node gets an acknowledgement from the inbox.
Well, in fact, what I would do is I'd probably just propagate it. I would piggyback it on. The details of how you do that are up to the implementation. I would probably just piggyback it. So in other words, when the tail tells the head it's confirmed, then the head in each packet to everybody else says, okay, everything up to this point is confirmed, or here's what I've seen confirmed, or here's what's outstanding and not yet confirmed. Those are just different variations of the same thing. But that becomes a protocol optimization. From a simple perspective, yes, the tail just sends a message to every one of them. You'll do that, and then you'll go, wow, this is a lot of extra messages, and you'll say, could I cut those down? And then you'll simplify it and say, yeah, I'll just piggyback. And that's how you'll end up with 80% fewer messages. With a small trade-off there, because it's going to take a little bit longer for it to propagate, but 80% fewer messages is a lot. So in CRAQ, you can read from the middle. So client A reads, does a get, and they get the clean version. But client B, who reads and does a get and sees that the clean version is version 3, the dirty version is version 5, we don't know. So it comes over here and reads. So client A saw that value and it was only clean. It read before the change started propagating through. So if the node you're reading from thinks that the value is clean, it just returns it. If the node you think you're reading from the value is not clean, it either has to go and check it with the tail, or it has to tell the client to go check it with the tail. The effect is the same. If you really build these things in, I was just going to say, if you really build these things in the real world, what will happen is we'll put a proxy service in front of it, and that forwarding to the tail, you won't even see it as a client, because what will happen is it'll get routed to S3. S3 will say, oh, I can't tell you, you'll have to go to the tail. We'll just simply forward the message to the tail. The tail will make the decision and then send it back to the proxy server. That minimizes the number of extra messages that get exchanged. But that's an optimization that would be applied in a real world case. If we don't have a proxy server in front of it, then someone has to send a message over here. Whether it's I send a message to client B and tell it to go over to the tail, or I send a message to the tail and say what version, and then I tell client B the right answer.
How do I know when to put it, let's say I'm S3, how do I know when it's clean now, like when it's coming from?
I'm going to get a message that says,
From the
this is, well, that was the conversation we actually just had, which was the simplest protocol is S5 says, it sends a message to everybody. You can do it chain back the other direction, you can do it as directed unicast or as a broadcast packet. But basically, S5 is going to say, okay, everybody, I've now recorded version 5. And version 5 can now be marked as clean. Or what I pointed out is, one optimization is S5 has to tell S1 anyway, so it could just simply say to S1, it's clean, and S1 can then, in its next message to S2, say, oh, and by the way, D5 was committed. But those become implementation elements. Conceptually, the protocol is the same. We're just arguing about how we implement the protocol to minimize the number of messages we're sending. And that's the problem with looking at protocol implementations that people who optimize. You look at them and you go, what? Why are you doing this? Because something that was obvious at the time they did the optimization obfuscates what's actually going on at the protocol level. And you will find yourself doing that. And you will be able to walk back and look at that code and say, I know why we're doing it that way. But if you walk into an existing distributed system project and you start looking at it, you'll be like, what? Why? And you'll feel lost. And this is one of the realities of looking at almost any actual implementation of distributed systems. You need to understand the algorithms before you can understand how they've been changed by the implementation to minimize the number of messages that get exchanged. Because over and over again, the thing that is most expensive in these systems are sending messages. So when does a version become clean? Which is a question that people have been poking at here. So write propagates down the chain. The head receives the write, marks it dirty, sends it to S2. S2 marks it as dirty, sends it to S3. The tail receives the write, marks it as clean because I'm the end of the line. I'm the one who gets to decide. Everybody has it because I got it now. And he then sends an ACK. You can send it back up the chain. That's what this is suggesting. That's probably what the paper actually did. He sends it back up the chain, or you can send it to the head and have it propagate down. I don't think there's actually any net effective difference between the two. And then each node on receiving the ACK can mark their version clean. Now, if you're sending it back up the chain, the node that gets it marks it and then sends the clean notice to the previous node. That's a very simple model, I think. But it doesn't matter. You can make it work in a variety of ways. So, the beautiful thing about this is that in steady state, when there's no writes in flight, all the versions are clean, and therefore, a burst of reads is satisfied by spreading it out. And this gives you much better read functionality. When you get a burst of writes, then the nodes near the head have dirty versions are going to actually be the ones who bounce it to the tail. But keep in mind, that only applies to the values that are currently dirty. If your database is 50 million entries, and 5,000 of them are dirty, you may not hit any dirty writes. In the Twitter example, which is back to the power law distribution, what really happens is, yeah, it turns out you end up hitting them a lot. Because the things that people are reading are the things that people are writing. But that depends on the workload. If you actually had a workload where you never modified anything, so I did this recently. I built a database front end that has no delete and no update. You can insert objects. That's it. You can look them up too. You can insert them and you can retrieve them, but you can't update them. Why? Because reasoning about immutable data stores is actually quite different than reasoning about mutable data stores. Making something immutable essentially makes it permanent. And a system like this, that permanence, perfect. You'd always be able to do the right thing. Because if you can read it, you don't even have to check. You just return it. But that's a very specialized case. Most databases are going to be implementing CRUD operations, right? People know CRUD? Create, read, update, delete. Typical database interface. In a key value store, you'll see that. Put, get are the two big ones. Because put operates as a create or an overwrite. Get is your read, and then usually we'll add a delete, so you can delete keys. And that's a key value store. 3 operations. So dirty versions are transient, the act cleans them up. So that's the point, is that if you get a burst of writes, then this will propagate them through, it'll clean them up. If your write traffic is more continuous, this may or may not be the right solution for you. All right, so now here we go. One more checkpoint. I think this is the last one today. A client reads from S2. The version is dirty. S2 asks the committed version to get S7. We'll do 3 minutes this time. Reason about this.
Maybe the new wrinkles are edited. Yeah. Depending on the definition of
All right. So, is S2's response consistent? Yes? Why?
Because like, so W8 or write 8 could affect D7, but at that timestamp, it would still be the value that it.
Right. So this is, again, the observability issue. Remember when we talk about consistent cuts, we can return a value that is stale after we grabbed it, but it's still consistent. What consistency model does it give us? Which is kind of a trick question because we haven't actually formally talked about all the different consistency models, which is always a very confusing kind of conversation. But this gives us the easiest one. It gives us the same one that Paxos gives us, which is linearizability. In other words, we have a linear order in which things change. But linearizability happens because it's decided at the tail. In Paxos, linearizability happens because we reach consensus to get a quorum. Once we have the quorum, we have linearizability. Anybody else who goes and asks what that value is will get the same answer. So every read returns a value that was committed at some point during that read. If you wanted to have conflicting read-write operations on the same value serialized, you have to implement that at a higher level. We are not solving that problem at our level. Our level is a stateless one. Put, get. If you do a get, and I'm doing a put, and you can literally write this code. We write to the same value back and forth, and then so you're reading it, I'm writing it. You actually won't know what the value, what the actual order was, because this is going to all happen down inside of the hardware underneath us. Same thing happens on the network. If you need serializability at that level, between operations that read and mutate the same value, you have to build something on top. If you write two threads that write the same value in memory without a lock, the result that you get when you read it is in fact not predictable, but not the hardware's fault. If you wanted a value that was the same when you get it, you have to add extra structure around it. And I've had this particular conversation many times with people because they'll say, oh, but you need to do that. You need to provide this extra level of guarantee. I'm like, I don't have any idea. I'm responding to a read. I don't have any idea how you're using it. This is the guarantee I provide. If you want a stronger guarantee at a level above me, build it yourself. And that's what people do. That's why you end up seeing things like Paxos in the configuration manager and CRAQ in the database. They're not mutually exclusive. They're different turtles. They're stacked on each other, but they're still just different turtles. I bet you're not old enough to know that particular reference, though. Anybody know the turtle reference? It's turtles all the way down. Fred Patchett, Discworld. Anybody know Fred Patchett? Discworld? Yeah, it's literally a description of the world. The world sits on the back of a turtle, and then I think it's a kid. The kid asks his dad, "Well, what's the turtle standing on?" And he says it's turtles all the way down. And that's the metaphor here. So CRAQ provides strong consistency guarantees. The tail's the authority. CRAQ just avoids asking it when you don't have to. That's our efficiency hack. This is actually a really fast implementation for a broad range of workloads. And it still maintains strong safety guarantees. So let's put this in the context of everything we've been talking about. We spent a lot of time talking about Paxos and quorum intersection and how to adopt leaders and make ballots and reach consensus. Now we're saying, wow, can we do this a little bit easier than Paxos gave it to us? I spent a lot of time on Paxos because I really wanted you to understand how what's really a simple problem isn't that simple when you try to reason about it. When you try to take something that is inherently not ordered and say, I'm going to make this do what I want. I'm going to make it ordered. But we can achieve that in different ways. This one has the same goal, strong safety, but achieves it in a more structured fashion. So we've constrained the problem. There's lots of places where I wouldn't want to use this. I wouldn't want to use this for my Martian data center. I'm going to put my tail on Mars. It means it's going to take 44 minutes sometimes for me to actually get the acknowledgement back that this thing has been hardened. That's a really big window to leave open. Doesn't work well there. That's a recurring theme that you will see when you build distributed systems. You don't get to just reach into the tool chest and say, Paxos for everything. But you also don't get to reach in there and say, CRAQ for everything. You don't get to say RAF for everything. You have to make conscious decisions about the trade-offs and realize the reason that people end up re-implementing these things over and over again is that the design space is actually quite large and the trade-offs are nuanced and not always obvious until you've built it 3 times. See, the first time you build it, you make all these mistakes. And then you make the mistake the second time of going, oh, I know all of those mistakes and I'm going to design around every single one of them. And the second one turns into this 6-headed, well, 12-headed hybrid thing that's really complicated. It's called second system syndrome, where literally the second version you build is too complicated. And then the third version you build, you get rid of some of that complication, but you start forgetting the things you learned in the first one. So you repeat mistakes. Chain replication isn't a replacement for consensus. It just simply simplifies one of the hardest parts about consensus, which was the configuration piece, which I kind of hand-waved over. That is essentially what leader election is. It's the configuration. But then when we wanted to change the network topology by adding additional proposers, acceptors, or learners, then we had to actually build a configuration service on top of that. That's our turtle stacking metaphor again. I'm not going to do this. We don't have time. Even when I looked at the slides last night, I was like, I bet this isn't going to quite fit. That's good. That's okay. You know, think about it. How would you do this? How are you going to build that 5-node chain? How are you going to deal with that failure? Because this is really the right question to be asking yourself. Do I understand how CRAQ would work? How I would actually implement it if that were what I chose to implement for my capstone? I'm going to build the best CRAQ ever. You know, you can make it home. You can get a CRAQ house. But I'm fucking, that's a CRAQ home. Dad jokes don't get any better. All right, so there you go, debrief. So now a question here for you to consider. You're running a chain replicated key value store. The client says, my writes are succeeding, but reads return stale data. Where would you start looking? I love these questions because this is the debugging question. This is the, do I understand the system well enough to know where to start looking under the hood? Maybe it's the smart plugs that are bad. It's a diesel engine. Which nobody will understand. Exactly. That used to be the old joke. One of the old jokes that I heard from my old switch was, you know, you can go get a job changing spark plugs in diesel engines. And if you don't know anything about internal combustion engines, you won't realize that they use compression, not electrical sparks. Pointless. So think about that. I'm not going to go through that here. I'm going to leave this as the question that you should think about when, I don't know, you're on a walk, you're in the shower, or you're like you need a distraction from some other class that is boring. Where do I look? And then it gives a big hint at the end, right? Think about what would happen if the configuration service were wrong, or the configuration view the client has at this point in time is wrong, because those configuration views are cached. So how do you know when it's time to refresh your cache? So, big recap over the last, 5 or 6 lectures, which is you don't need voting for everything. That whole thing of writing from the head to the tail is actually pretty powerful. It's a pretty interesting idea. Reading from the end of our chain or reading from the middle of our chain if we're using versioning. The commit point, even in CRAQ, the commit point was always the tail. So we didn't change the base model. What we did was we changed some optimizations of how we could use this. Failure handling, the head, the middle, and the tail are different cases. They all rely on knowing what's been committed, the prefix invariant. I think that's because the paper originally actually described this as appending to a string, which, if you think about it, is just a log, right? You're appending to a log. That is just a string that you keep putting suffixes on. So the whole idea here, the whole lattice connection, and then the idea here is, remember I said there's lots of different ways to achieve the same outcome, and you can drop different paths in there without changing what actually is happening. This happens a lot in distributed systems. You build this replicated database with this nice clean front end. How you implement it under the covers is in fact just different paths from nothing to working service. And none of them are necessarily invalid, and none of them are inherently superior to all of the others. Almost always a path from what am I going to build to here I've built something is very much driven by the trade-offs that you make in deciding what you want to optimize. Let's see, for Thursday we're going to talk about Dynamo, which is in fact a key value store. And there's the optional paper, Consistency Non-Transactional Distributed Storage, which is a lot newer. We're going to be talking about consistency models next, because I've been talking about, eventually consistent and linearizable and whatnot. So naturally, we're going to hit that on Thursday to try and bring that one home. Now that we've been looking at this and we've hand waving consistency models, we'll actually nail them down. I think that's pretty much it. I'll see you on Thursday.